Executive Director of the Louisiana University's Marine Consortium, aka LUMCON. And I'd like to thank you all for joining us tonight for the first talk in LUMCON's new online science series. Every Thursday night at 7 p.m. Central, we're inviting a Louisiana scientist to share their research. And of course, we're going to give you the opportunity to listen and ask questions of some truly amazing people doing some truly extraordinary science. And I hope you will continue to join us each week as we explore more of our world from the comfort of our homes. And you can find more information about the complete series at our website, lumcon.edu. All you need to do is just scroll down our homepage to the link under the news events. Tonight, it's my privilege to introduce Dr. Alex Kolker, who's the Associate Professor at LUMCON. Alex is a coastal geologist, and I will brag on him a little bit that he's the 2019 and 2020 Fulbright Scholar as well. He has studied sea level rise and coastal impacts for almost 2 decades, and he works at the intersection of policy and research, and he's dedicated to making our coast here in Louisiana more resilient. He often works educating the public about coastal issues and climate change, and of course that's a big part of those efforts. Alex's research focuses on the dynamics that govern 4 major components of coastal change. That's climate change and sea level dynamics, pathways of sediment and water transport, subsidence, and how human dynamics govern and are governed by a changing coastal environment. So please join me in virtually welcoming Dr. Alex Kolker tonight. Thank you.
All right. Well, Craig, thank you. Thank you so much for that introduction, and thank you all for showing up here this evening. You know, we were talking earlier, and we were saying, you know, it's a shame that, or it's difficult that a lot of us can't get to the coast. We can't get to LUMCON these days, and you know, these are unusual times. But what I'm here to tell you is there are a lot of ways that you can look at the coast from the comfort and safety of your computer. And these are things that we can do in unusual times like this, but there's also ways that these tools are freely accessible and easy, relatively easy to use, and they allow us to look at the coast, you know, on any given day. And so that's what I'll be talking to you this evening about. So I'll call it Adventures in Monitoring and online tools to watch Louisiana's coast from your desktop. You know, a lot of people think that Louisiana's coast, that looking at the computer is more like what we have on the left-hand side. It's, you know, Dilbert and his dog looking at the computer and kind of a humdrum situation. But actually, that's not really the case. There's a lot of monitoring systems, and this is just a little bit of our monitoring system here in the middle that allow you to see the kinds of things that we have on the right, and that's actually data from the Mississippi River, which is really cool and really interesting information about how our coast changes. And of course, this is really important here in Louisiana because we have one of the most dynamic and complex coasts in the country. And so being able to observe it and watch it is both neat and it's also useful, right? So just to put this up there, why do we need to use coastal data? It actually has a lot of really interesting uses and important uses. So one use, and maybe the most important use, is that it helps us reduce risks during floods and storms. You know, we all know that Louisiana is prone to floods and storms and difficult situations on the water, and having online data of water level records is crucial both for emergency managers and for general members of the public to be able to prepare for floods and storms and to be able to know what's going on our coast in its challenging times. It's also useful to understand the rates and causes of coastal land loss. You know, we've all heard Louisiana's losing land. We can actually use online tools to look at that land loss. It's useful to evaluate coastal restoration projects. So this photo here is of the Davis Pond diversion. You know, people have asked a lot, are diversions working? Are they not working? How's this project or that project working? And one thing is that there's a lot of tools that are available for you to look at that information on your own and for you to see what's happening on your own. And for you to make up your own mind about some of these questions. Of course, there's other reasons. It can help guide fishing expeditions. So there's a lot of information about water levels and temperature, and anyone who's fished along the coast knows that, you know, when the fish bite is, or relate is, you know, it's driven by the weather and water levels and temperature. And we can actually use this to guide fishing. Don't tell my boss, but I look at the Lumcon weather gauges to know whether or not to go behind the dock at Lumcon and go fishing. Don't tell my boss that, but I do. But there's other uses too, right? We can use it to study climate change and subsidence and sea level rise. So our climate is changing. A lot of people have questions about how fast it's changing and what this means. And there's online tools that'll allow us to do that, to monitor climate change and sea level rise. I won't talk too much tonight about air pollution, but there's a lot of water data. There's a lot of air data online too, and there's ways to access this online air pollution data. Of course, scientists, it helps us plan field investigations. I often look at these data if I'm going out in the field to know where and when to sample. And of course, it's also useful if you're just curious. It's like I said, this is where we live. It's a beautiful, complicated coast, and so anyone who's interested in finding out more about it can find out more about our coast, can do it online. So I'll start off with how we look at Louisiana from above and from remote sensing. So when we talk about remote sensing data, it's data that's, if you want to get technical, it's data that's collected from a sensor that's far from the place that it's being measured. This often is things like satellites or aircraft, or more recently drones that are equipped with sensors. The science of this is that these sensors typically measure light or radio waves, and they turn this information into an image or a map. One nice thing about the remote sensing is that it covers a wide area. Sometimes the resolution is great, sometimes it's not so great, so the resolution can vary, depends a little bit on the satellite, but it often covers a wide area. It's great about covering a wide area, but it does have the limitation that it only measures, typically only measures the land or water surface. If you want to find out about what's happening under the ground or under the water, you often need to send out a boat or a field crew to look at what's happening underneath. And it does have the limitation, environmental conditions like clouds can obscure the data. So we'll start off by looking at Louisiana from above. And so NASA has a worldview tool that allows us to look at planet Earth. And so it uses what the base layer uses, what's called the moderate resolution imaging spectroradiometer. Great title. We often just call it MODIS. It provides daily true color images of our planet. You can actually use this tool and do more complex analyses, but we'll start off by looking at it from February, from this year. So let's see if I'll pull it up. This is NASA's worldview tool. This is the tool today. This is actually Louisiana today is what we're looking at. Let me see if I can find my cursor. There's my cursor's gone for a second. There's my cursor. So we will look at, this is Louisiana today. This is the Earth today. This is the Earth, what it looks like. This data goes back for for over a decade. We can actually add, if you look down here, so down at the bottom of this, there is, down at the bottom of this, oops, excuse me. If we look at the bottom of this tool, we can actually find, we can have a time tool that allows us to adjust the date. And I happen to know that late February was a good time to look at Louisiana's coast. So I can go back and I can go to February 28th. And I know that this was actually a pretty good time to look at Louisiana. It was a good time because there weren't a lot of clouds. And so we can zoom in, and I can just use my mouse to zoom in. I could also use tools over here. There's a little plus arrow. We can actually look at Louisiana's coast online, and you can see some pretty neat things. So you can see a big, let's see if I can use a pen, and we can look at the mouth of the Bird's Foot here, and you can see a big plume of dirty water. That's a lot of sediment. The river's been high this year, so you can see a big plume of dirty water. We can look over at the Atchafalaya River and see a big plume of dirty water over here. Again, the river is high. You can see that that a lot of this has been blown out to in this direction, right? It's been blown to the south, to the southeast. That's given largely by winds. You can also see other rivers that are in flood. So we can actually look at the coast and see it like this. I'll clear these remarks and we'll look and just see what the world looks like when we don't have the world in flood. So last summer, of course, at late summer, Louisiana was, the river was low, and we can look at what the coast might look like on a different day. So we can go to, and I happen to know in 2019, September of 2019, I can click here and go to early September of 2019 and see what our coast looks like when there's no river in flood. So now September of 2019, the river was low, and so we can look again at the mouth of the Bird's Foot, of the mouth of the Mississippi River here, and you can see not a lot of sediment. We could actually zoom in just a little bit, and you can actually start to see some of the channels of the Mississippi River over here. Can clear that. We can see the Atchafalaya River over here. So if we go over to the Atchafalaya River, we can see over here. You can actually see right here, you can see the Wax Lake Delta, which is one of the few areas in Louisiana that's building land. You can actually also see the Atchafalaya River Delta right here. So we can start to see areas in the coast that are functioning and building land. You can almost even make out a little bit of Lumcon. We're right about here. So I'll clear these. And we'll go back to the presentation. That's not okay. So let me go over it and move to the pointer, and that should get me there. Perfect. And we'll view the slideshow from the current slide. Great. And let me clear out these pen markers. So great. Another tool that we have is we can use Google Earth. So Google Earth is a really nice tool. There's a simple version that is web-based and a pro version that you can download and install on your computer. I am going to use the pro version tonight because it has a few more features that you can show. And one nice feature that it has, and that I'll show you in just a minute, is it's got a time slider that you can use to see recent coastal change. And it's got a set of measurement tools. So we'll go over here to Google Earth. And I'll pull up Google Earth, which is right here. So Google Earth, you might just think of as a digital map. So here's a digital map of the United States. And I'll zoom in like this. It's beautiful. You can actually see the Mississippi River Valley here. You can see the Red River Valley over here. And I'm going to zoom in to one of my favorite places, which is West Bay, which is down here at the mouth of the Mississippi River. West Bay has an interesting history. It's a diversion. So it's one of these areas where they've cut a channel into the Mississippi River, hoping to build land, hoping that you could divert sediment and build land. They opened it in about 2002. And for the first 7 years or so, it didn't build a whole lot of land. And then after about 2009, they were just about to close down the diversion, in part because it wasn't building land, and in part because they thought it was leading to shoaling. It was sediment was building up in an anchorage. right here, and boats were beginning to run aground. They almost closed the diversion and they pumped, but before they did, they dredged the anchorage over here and they created some artificial islands in West Bay in here. And that seemed to have changed the hydrology of the bay and changed the way sediments accumulated. And we can actually take a look at that. So I'm going to zoom in a little bit on West Bay, and I'm going to go to this time tool that's up here. So if you can look, and I'll just do the highlight or the arrow. If you take a look right here, right there, there's a time tool, this little clock. If you see it, we can go to this time tool, go back to the pointer, and I can go to this time tool, and it can actually, I can get maps of West Bay from different points in time. We can see down here, if you can see the imagery date, that's the date that the photos were taken. So you can see in 1998, the bay was almost all open water. We click through, we can see this is again 1988, the bay's open water. I'll move forward just a little bit. And we can go back to about 2000. That's interesting. 2004, you can see the bay is almost all open water. You can see right here, you can see the diversion. If you see that little cut right there, actually the diversion's more like right there. You can see that little cut. You can see the bay is pretty much all open water. We'll move the time tool a little bit forward. 2007, you can see there's a lot of sediment streaming through the bay. So you can see all this sediment streaming in here, these sediment streams here. You can also see not a lot of land that's being built. If we go through and look at another time slice, let's say 2010, you can actually start to see the islands that they put in. So these are the artificial islands right here that they started to put in. And if we start to look at 2012, you can actually start to see more land is beginning to emerge. And if we go to 2016, we can actually take a closer look at this land. I'll zoom in. Let me clear out some of the my drawings. And I'm going to zoom in, and I'll go to one other thing, which is the measurement tool. So this measurement tool is right here, this ruler, and I can go to this ruler and I can click on it, and I can do a line. So I could measure the length of the Mississippi River or the width of the Mississippi River. So I can draw a line like this. Says it's about 3/4 of a mile long, so you can measure things. And I can go to the polygon tool, and I can actually measure the area of something. So I can click around this island like this and outline this island. I'm going to try to do it just a little bit of a basic job. It's not perfect, but it's a basic job. And it can tell me the size of this island. And this island is about 242 acres. And this is actually a way to, measure land growth and land change. So people have asked this question: Are we, we all know we're losing land. A lot of people want to know how fast, and are some of these coastal restoration projects effective? This is a tool that you can use. It's similar to the tool that people use across the state to get at this question. You've heard a football field, the statistic, we lose a football field of land, every hour. The people that make that measurement do something similar. They often rely on automation to make the job run faster and a little bit more standardized. And they use make a lot of measurements based on a lot of images. More repeatability gives you a better number. But this is a way to do it, and it's a way that you can look at land growth from your home computer on your own. So with that, I'll go back to our slides. So So this is just, again, a little history of West Bay, a little bit of a history of these, just a comparison of what I did to what others do. We can also look at questions like how warm is the water in the Gulf of Mexico, right? So it turns out that the LSU's EarthScan lab and Nan Walker and her team have done a really nice job of putting up images of our remotely sensed images of our coast. And so they can actually look at the temperature of our coast. They can look at it above based on the wavelength of light reflected back from the Earth. And so we can take a look at these data. So I'll just go back here, and I will go back to the LSU's EarthScan lab, and I pulled up an image of the coast from March of this year. And so what we have here is an image of the coast in March of this year, and you can see there's a lot of cold water out from Louisiana's coast. A lot of this is related to water coming out from the Mississippi River. We can look at, you can actually see like cool little features like this, like little plumes or eddies that are coming off the river. So there's a whole lot of really cool features that you can see. You can see it gets even darker over here by the river. So really cool features you can look at. They put up this scale over here is the temperature in centigrade. So we can look at this. You can also look at different times of the year. So we could look, for example, at the summer, and just if we wanted to look at the August, let's say, of 2019, just to give you an example, you could look at August of 2019, and you could see the Gulf is much hotter. Hurricanes start to form at about 20-something degrees C. So you can see this is the Gulf of Mexico, and a lot of it is conditions where you could get a hurricane. It's not surprising news, but this is information that you could look at on your own. So cool pictures of the Gulf of Mexico. Are there any questions up at this point? We're sort of done with this first part of the talk. Mert, have any people logged in and asked questions?
Mary Miller says that it's super cool, but no questions. So you must be doing a fantastic job.
Awesome. Well, super cool is the best thing that you can hear. So now we're going to talk about in situ sensors. So we talked about sensors from satellites. We'll now talk about sensors that are located in the water, right? So there's sensors
Alex,
that are in the water.
Alex, yeah. I'm sorry, we're starting to get some questions, and it just took some people some time to type, I think.
Great.
So Devin was wondering how you would be able to download the data for use in GIS. Is that possible for me?
Absolutely. A lot of these data that you can download, a lot of these data. That sort of gets into 102, and that's the back end of it, but a lot of these data can be downloaded for GIS. That's a longer answer because it just gets into some computer downloading, but most of these places allow you to download the data. I can actually show you some of the easier to download data, but much of it is downloadable. So great question.
And then Devin says awesome, thanks. Jason had a question about, I think, links and if we're going to make them available. So just a reminder that when you logged in, you should have gotten an option to download the list of links that Alex is going to tonight. If you did not get that, that's fine. We will put a link in the thank you email you'll get in about 24 hours from now. But we'll also put it on our Science Talks webpage on our website. And that's easy to find if you go to the LumCon website. On the home page, it's the link for that particular page on our website is in the news and events section. So you'll be able to find that.
Great. So yeah, there's also thanks, Mert. So there's also in situ sensors. So there's sensors, instruments that people put out on the water that measure air and water. So these things can measure things like temperature, pressure, depth, air and water speed. The nice thing is that they measure one area really, really specifically. Then the question is, how do you extrapolate this to a wider area? But this is maybe the big picture is a picture of a platform where we've got one of our LUMCON sensors, and the picture in the upper right is what a sensor might look like. So we can, so the river is in flood right now, and we can actually look at what it looks like. So I'm going to go to the USGS's gauge. They have a gauge that measures at the Belle Chasse in the Mississippi River at Belle Chasse. So just to show you where it is, it's right here. This is where the Belle Chasse gauge is, and I'll go to it right here. Oh, oops, actually, I've got, sorry about that. I'll just tell you what we're going to measure, what we're going to see. It measures discharge, which is how much water is moving in the river in cubic feet per second. Measures the height of the water, just relative to a local marker. It's got what is called stream level, which is basically the water height relative to a specific geological or engineering marker. That's basically the sort of a geological or engineering version of sea level. That's called the North American Vertical Datum, or NAVD. It also measures turbidity, which is basically how dark the water is. And typically that's measured with an underwater sensor, with like a light sensor underwater. And scientists can convert turbidity into amount of sand and mud by comparing this value to an amount of sediment in water samples. It also measures the velocity, which is really the speed and the direction of the water. So if we go here, this is the page where we're at, and I'm gonna have, and you can actually click on these samples. You can actually ask the computer to request data going back as far as the instrument's been around, which in this case is since about 2008. But I'm gonna have it show things since December 1, which is about when the water started to rise. So I could just enter that information into the tool that it gives me, and I'll just click go, and I'll let it come up with this information. It's got to think about it for a minute, which is okay. This is the real world. Computers have to think sometimes. And we'll have it come up with this information, should come up in just a second.
Hey, Alex, while we're waiting for that to happen, we had a suggestion from Todd. Todd's asking if you can use a different color when you draw on the screen. He's having a hard time seeing the green.
Yeah, sure. I'll see if I can use a pen, and I'll see if I can use, can I choose a color? Choose pen color. Yeah, let's do, I'll do red. So, okay, great. So we are, I'll go back to the pointer, or actually we can use the pen. So we've got, what we have here is the discharge. So this is discharge right here in cubic feet per second. And you can see that the river was relatively low, was about 500,000 cubic feet per second in December, which is about average. It reached over 1 million starting in early February, and it's been climbing slowly since. We can look at the height of the water and the height of the water relative to the gauge, and you can actually see its water's been rising, and then it's been relatively stable with a few fluctuations since. You can actually see these little things in there. Those are actually tidal fluctuations, so kind of cool. Stream water elevation, which is basically the same information. And we can see the turbidity, which is kind of cool. So you can see the turbidity spikes here at the beginning, right? You can see two spikes in turbidity, one early season, one late season, and then down here, it's relatively low. What happens here is that the river, when it starts to flood, it pushes up all of the easily mobile sediment at the bottom of the river. And then after the river's been flooding for a long time, it tends to run clean. Not unlike what might happen to your street if it's been really dry, then you get a rainstorm, you get a first flush of mud on your street, and then after a while, the street runs clean. This actually has implications for diversions. We talk about diverting the Mississippi River in Louisiana. Typically what this means is you're going to get a lot of sediment. You're going to get your most land building in this part of the time. And then over in this part of the time, you're going to have a lot more fresh water, but a lot less sediment. So you might want to open the river during this time, a diversion a lot during this time, and then scale it back during this time. So that's just one thing that we've got. We've actually, the river, I don't know if you heard it, the river is, they've opened up the Bonacary Spillway, which is a relief valve because the river is really high. The Army Corps actually puts up their data from how much they've opened up the Bonacary Spillway. So they put that online. So here is the data for this opening. So we're now looking at the river, the spillway's been opened to, they've opened up 50 bays and it's moving at 50,000 cubic feet per second, which in Louisiana is not all that much water, but that would actually be one of the 10 or 20 largest, probably one of the 20 largest rivers in the country if it was its own river. So a whole lot of water. We can monitor I'll get to this. We can actually monitor coastal flooding. This is Lumcon in a day that we had high water. We get high water on the coast. It's something that we all need to deal with, and we all need to understand. And there are ways to understand it with online data. So we can go back, and we can go. There's the National Oceanographic and Atmospheric Administration runs a gauge at Grand Isle, and they'll show you water level predicted, the observed water level. They'll show you the predicted water level, which they do based on calculations based on the moon and the sun, which really what drive the tides. They can measure, a lot of these gauges will measure things like water temperature, wind speed and wind direction, and long-term trends in sea level. So we can go and take a look at this gauge. Whoops. And here is the home page for these data. I'll go show you, this is where we can go and take a look. This is what the data looks like right now. This is just recently. So red is the observed water level and blue is the predicted water level. You can see water levels are just a little bit higher than average, than predicted. There may be a couple inches higher than predicted. I'm going to go to one time in March when we had a cold front come through. So we can ask to search for this data. So I'm going to go and have it plot this up. It tells us we can put it in standard or metric units. We can compare it to a time zone. We'll make it local standard or local daylight time. And we can plot these data. This data has been verified, so what was red is green now. But you can see it right here. This is, did I put up a pointer? This green is the observed water level, and the blue is the predicted water level. You can see that the water slowly, if we look at this, it slowly rises relative to what's predicted, and then starting here, it drops, and it's actually a little bit lower than normal. What happened? We can actually look at the meteorology, and we can actually look at the wind. Oops, go back to the pointer. Go back to the winds from this time period. I've got the winds for this time period up, and you can actually see. Look, we just look at what it's saying instead of looking at the arrows. You can see the arrows, but I'll show you at the beginning of this time period there were winds out of the south. So those winds out of the south, they blow water on shore, and the water tends to rise. And then a front comes through, and there's winds out of the north. So here the winds are out of the southeast, and they're at about 6 knots. If we look over here, the winds are out of the north. They are blowing at about 17 knots, so that's about 20 miles an hour, and gusting to 20 miles an hour. If we go and take a look at this data and compare the time that the water level shifts from being above normal to below normal, is that time when the wind shifts. And so this is a common thing that happens. When winds blow out of the south, they force water onshore. It tends to be really hot and sticky. And then the winds shift, the front comes through, the winds shift, and the winds come out of the north, and you blow water offshore. This is actually what's happening today. It's kind of hot, kind of sticky. The water is a little bit higher than normal. We're going to have a front come through overnight, and I'll bet that the water levels drop overnight. So maybe depending on the timing of this front, I might send that out as when Mert sends out a thank you email. I might send out a graph just to kind of give you a bonus graph to show you what happened in the last couple of days. We can also look at things like, oops, if we go up here, we can look at things like sea level trends. So if we go back here, we go to water levels, we can actually look at, go here, we've actually got data. This gauge has been running since like the 1940s. And we can actually look at, go to here, look at this tool that says sea level trends. And it'll pull up the sea level in Grand Isle, and sea level, it will tell us how fast sea level has risen in Grand Isle since the 1940s. And it's right here, it's this number, it's 9.13 millimeters a year. So about a half an inch, a little less than a half an inch a year on average over the last half century. We could compare that to another place, and we could compare it, for example, to Pensacola, in which case the rate is about 2 millimeters a year. People asked about the data. You can actually get these raw data, so I could go and export this to text. Of course, the reason that sea level is rising faster in Louisiana than Pensacola is Louisiana, we're sinking. We're this delta, we're all this soft mud. Pensacola, it's Florida, it sits on hard rock. So sea level, the rise in sea level is mostly just the global rise in sea level. So that's the reason. We can actually export this data. So people asked about exporting these data. You can actually get the raw data, and you can do science with it. So people ask, can we get the raw data? And the answer is yes. And you can actually use these data to look at trends in sea level around the country, do real science. I actually use these data. I did some analyses on these data and published it. So working scientists use these data. If there's one last place we can look, you can also get things like water quality data. So LumCon, we actually have water quality data at LumCon. So in addition, so we can go, this is our LumCon weather monitoring page, and we can go to our real-time data at LumCon, and we can see, again, we've got some of these same parameters, wind speed, meteorology, air temperature, water temperature. We can also look down here and we can look at things like dissolved oxygen and chlorophyll. So, you know, we're very concerned. Certainly my colleague, Nancy Rabelais, has spent her career looking at dissolved oxygen in Louisiana. We can start to look at things like dissolved oxygen. And of course, oxygen is produced by algae. Algae use chlorophyll. So we can look at the relationship between dissolved oxygen and chlorophyll. So for example, right here, you can see they both go up at the same time. So more plants in the water, more photosynthesis. Photosynthesis produces oxygen, so more oxygen. So, and we can compare that to, let's say, for example, what is up here, and maybe water temperature. So perhaps there's more plant growth because it's a warmer time of the day, and maybe their plants are growing better in the sun. So we can start to look at some of the relationship between the physical processes and the biology. So we can start to understand how these ecosystems work. So there's a lot of tools that we can use. And again, some of these data are here, and you can actually use the data. You can download the data and again, do analyses based on these data.
Hi, Alex. We have another question going back just a little bit. Jeffrey is asking if the water heights, I guess, were all sea level rise, or does that take into account the sinking of the Earth's crust?
Great question. Great question. That is what we call the relative sea level rise. So that is just the water. That is the combined motion of the global sea level rise and the sinking of the Earth. So Pensacola, the Earth is not sinking much, and that's why the sea level rise rate is relatively slow. So this is the rate of relative sea level rise. Excuse me, it's about 2 millimeters a year in Pensacola. Let me just draw that. Right. So it's 2 millimeters a year, right? If you can see this, and it's a relative trend. So that's both the land movement and the water movement. And in Louisiana, and if we go over, so Pensacola, which is not sinking, we have this relatively low value of 2.46, and in Grand Isle, we have this higher value that is 9.13, and and the difference between those two is the difference in the rate of sinking of Earth's crust. We're getting close to the end of this, so maybe I'll just show you the last thing. Just if you want, if you're tired of looking at data and you just want to see what's happening on the coast, we actually at LumCon we have a tower cam, and hopefully, I don't know, maybe we're a little bit late, but we might be able to catch just a little bit of the sunset. And so if there's nothing else and you're tired of watching data, you can look at the sunset, and you can look at the sunset here at LumCon. And with that, I'll just say thank you. I think our time is about up. And so thank you for listening. And I'll take any more questions that people have.
Thank you, Alex. That was wonderful. Jeffrey, thanks you too. So while you guys are busy typing in all those questions you want to ask Dr. Kolker while you have him at your disposal, I do have to announce that as part of this series, we're going to give out an award for people who attend 10 of these lectures. So if you attend 10 of these lectures, you will be sent a personal thank you from LumCon, and I'm not sure if we want to announce what that is. Dr. McLean, do you think we should announce what the prize will be?
I believe we should absolutely announce what the prize is.
I don't have one to show. I don't know if Tori happens to have one with her. But if you attend 10 of these lectures, do they need to be consecutive, Craig?
They do not need to be consecutive.
They do not need to be consecutive. You heard it from the director himself. If you attend 10 lectures online, or if we do these face-to-face, however you want to attend a lecture from LumCon, you will receive a Research Vessel Pelican Challenge coin. Do you want to explain to people what a challenge coin is, Craig?
It's a coin for challenges.
Yes.
The name sort of gives it away. So there are coins that are inspired, obviously, by the military, and in the last few years, they've become popular for sort of other organizations as well. They're a way to commemorate, things that are important in our lives and the connections and things like that we build. And we have a challenge coin that honors the research vessel Pelican, the pride of our fleet, and the pride of Louisiana. And so, yes, so those people who attend 10 of these lectures online will be sent a challenge coin from LumCon.
Okay, so we are having some questions come in. Are you ready, Alex?
Yeah,
pretty good.
great.
Carl is asking for an update, if you have any updates on the Elmer's Island restoration project.
I don't have any off the top of my head, but if you go to Google Earth, they do have historic imagery, and you can go and take a look at that for yourself. So you can go to Google Earth, and we can look at a lot of barrier islands, and you can see Louisiana's barrier islands are here. And actually, you can look, if we zoom in, you can see some of these places have had restoration projects, and I think you can actually see several of the restoration projects that are in place. So I don't have an update, but I would encourage you to go to Google Earth yourself and try and do this on your own.
Great, thank you, Alex. Ariel is asking about how the public gets involved with restoration projects.
So there are, I know the Coalition to Restore Coastal Louisiana does a lot of plantings for restoration projects, and I would encourage you to go and check out their website, because they do a lot of plantings and get people out in the field and planting marsh plants. And so I'd encourage you to check them out, and of course check out the data to see what's going on.
Mary is asking if Elmer's Island, if you know, Alex, is it still closed to the public?
I do not know the answer to that.
The last time I heard, it was still closed, but that was a couple of months ago. So that's as much information as I have. Ooh, this is a great question from Callie. Any advice for students trying to grow their proficiency in tools like these?
That's a great question.
That is an excellent question.
Yeah. So some of these tools they're freely available, and you can try them out yourself with trial and error. Also, a lot of universities have computer classes. So it does help to have a little bit of a computer background, learn some data management, data processing tools. And I would encourage you to incorporate these in class projects. I would say, it would be really helpful to take a computer course at your university. That's one thing. There are looking sort of the data tools. Sort of look for a course that's on data. There are the world of data is becoming more of a field of study, and so I would look at courses like that around your university. And it's possible that there could be more offerings from LumCon in the future on this if there was a demand. So it's possible that there might be more opportunities, and I might look at more opportunities to do this at schools in the future.
Ross is asking if sorry, I'm just trying to reword this a little. To clarify, if sea levels have in fact risen 1/2 inch over the last 40 years? And also, are there experiments or actual projects that are in play to offset the consequences of the rise?
Okay, so yeah, so we've got sea levels global. So Louisiana, Grand Isle, it's been about 9 millimeters a year. So I'll just make for almost since 1950. So that's, I'll just make the math easy. That's 10 millimeters a year. Let's call it a centimeter a year for what's that, 70 years. So that's 70 centimeters. That's about 2.5. That's about 2 feet. a little over 2 feet over 70 years. And that certainly is the case in Louisiana. The global rates of sea level rise are certainly less than that, because Louisiana, we have the total sea level rise is higher than the global sea level rise because we're sinking. And I think most people that spend time on Louisiana's coast know that we're losing land. And the sinking of the land is one of the reasons that we're losing land, along with the global climate change. And along with a few, of course, there's a lot of other causes of land loss as well. But the sinking of the land is certainly an issue, and the global rise in sea level is going up. The Pensacola rate of 2-something millimeters a year, that, because Pensacola is very stable, that's close to the global rate of sea level rise. In terms of projects, things to do to reverse that, a lot of our coastal restoration and protection projects are designed to offset this sea level rise. And of course, they're designed to offset a lot of things, including the land loss, some of which is caused by other factors. But a lot of the state's master plan, which involves diverting the Mississippi River, rebuilding barrier islands, direct marsh creation, and along with building levees and encouraging people to elevate their homes, all of those projects are done with an eye to this, the long-term rise in sea level that has happened and the continued rise in sea level in the future.
Thank you for that, Alex. Some information came in from Todd. Todd said that the CPRA will also have an island report coming out, hopefully in the next few months, about Elmer's. So hopefully we'll have something from CPRA soon.
Oh, that's good to hear.
Yep. And Todd, there probably won't be any rules to the use of the coins, but to get one, you just need to attend 10 LumCon lectures. So we won't go that far. You can use the coin just as a bragging rights if you want. Then we have a question from Jason, who's asking, how much has sea level rise contributed to the sinking of Grand Isle, and can we estimate how long it will be before we lose it or it disappears?
Yeah, so okay, so great question. So you know, we often separate that number that you saw, that 9 millimeters a year number, is the relative sea level rise. So that's the combined impact of the land sinking and the water rising. The global rise in sea level doesn't really cause the land to sink. The land sinks for other reasons. It sinks because it's soft sediment. It sinks because people have pulled oil and gas out of the ground. It sinks for other reasons by that. The difference between the Grand Isle gauge and the Pensacola gauge is, roughly speaking, that's the difference in the rate of sinking. So Grand Isle, the average rate is about 9 millimeters a year, and Pensacola, it's 2-something millimeters a year. So that difference is about 6 or 7 millimeters a year. That 6 or 7 millimeters a year on average is the average rate of sinking. And actually that paper that I showed you talks about the reasons why, and a lot of that seems, at least in Grand Isle, to be related to the withdrawal of fluids like oil and gas. In terms of how long it will last, a lot of that depends on the restoration efforts for our barrier islands. A lot of the CPRA, the state's master plan, is designed to take islands that could be lost in the very near future and prolong that by a period of decades. So the length of time that our islands stay around, it's in part related to the rate of sea level rise, and it's in part related to the restoration efforts of CPRA. Actually, one thing that's nice that I didn't show here, CPRA's master plan actually has their own data tool where they show how the coast will function with the master plan and under various rates of sea level rise for the future. And that's actually a very useful tool. And we could actually amend. I can send that out as another link if people are interested. But that is another tool that will allow us to look at the success of future projects with relationship to sea level rise. It's probably a whole nother presentation to go into it, but I can send out that link, and people can look at that on their own.
Thanks, Alex. That would be fantastic. A couple more questions have come in. So from Elsa, what are the effects of hurricanes on restoration projects? And does that affect the overall ability for that project to actually restore those areas?
Yeah, so hurricanes can be, they're actually interesting in terms of a marsh. They can be erosive, right? Because you've got a lot of fast moving water, and they can actually be, though, you can also get a lot of mud deposited on the marsh in a hurricane. If you were to go to the state's master plan data viewer, which we might be able to type in, if you type in Louisiana master plan data viewer, it will actually, you can actually come up with this. The models for the state's master plan, they actually include a series of storms in those models. And so if you were to go to this data viewer, which will show, which you can actually look at the success of various projects in the future. It will give you these. It will actually give you projections of land change in the future with these scenarios of high, medium, and low rates of sea level rise, and with and without the master plan. So we can put on with the master plan. And we can look at rates of land growth in the future. These models incorporate some level of hurricanes. Basically what they do is when they are running, they basically have some very complicated computer models, and they run the last 50 years worth of weather and storms for these models. And so these models actually incorporate they look 50 years in the future, and what they do is they take the previous 50 years worth of weather data and use that as inputs on these models. So they are incorporated here, and this data viewer will allow you to view these projections into the future. And so we can look at how the coast will change for 50 years in the future with land loss and land gain. And that actually does incorporate sea level rise and storms as well.
Great, thanks for that information, Alex. A question from Sierra. How many restoration plans have taken place? And if so, how, sorry, I'm losing words. How many restorations have taken place? And have they shown any effectiveness in building land?
Okay, so great question. The total number of restoration projects, I have to say, I don't know that off the top of my head. But actually, there is a website that actually lists a lot of the restoration projects that have taken place. And you can actually see, you can monitor the success of them. So the West Bay diversion was one. We can go and look at, and so we can look at other diversions. So you can look at, for example, the Davis Pond diversion, which my student Molly Kehoe did a really nice part of her PhD thesis on, and we can actually follow the success of this. A lot of these projects are, I won't get you dizzy in this data, but you can. This is the Davis Pond diversion. a lot of these projects are relatively successful in the short term. Their success in the long term depends, a lot of it depends on the rate of global sea level rise, and whether or not this rate of global sea level rise is fast or slow. So a lot of the projects have been relatively successful at building land at least the more recent projects have been relatively successful in the short term, and then their utility in the long term depends, a lot of that depends on the rate of global sea level rise.